The final topic we'll look at in Chapter 8 about multi-electron atoms is term symbols. Term symbols are a way of labeling different electronic states in multi-electron atoms. So when we consider the hydrogen atom, for example, when we're looking at the energies of the system, the only quantum number that matters is the quantum number n. And there's no real equivalent exactly for multi-electron atoms, right? N still matters, but now we have multiple electrons interacting with each other. So we need some quantum numbers that allow us to describe what's happening overall in terms of our system. And so the value in multi-electron atoms, the values for the different electrons of n and L matter, as well as the different magnetic quantum numbers, as well as our m sub L and m sub S values. So the spins matter because, as we saw in the previous video, we can't have any electrons that share all the same quantum numbers. That violates the rules regarding fermions, and that violates the Pauli exclusion principle, which is built on that. And so, how our spins are arranged inside of a set of orbitals will affect the energy of the electrons in that orbital. Okay, and so we characterize these different configurations in terms which have different energies using this idea of what we call term symbols. And so there are three quantum numbers that we use to describe this. And these arise from combinations of other quantum numbers that are available. So we have three quantum numbers that are capital L, capital S, and capital J. And let's explain what these three quantum numbers are. So capital L is the total angular momentum for our atom. I guess to be more specific, for the electrons in the atom. So total angular momentum. L can range from 0, 1, 2, etc. And we give these labels just like we do for electron orbitals for single electrons. So we call the 0, capital L equals 0, we call that a capital S term. And we have capital P, capital D, capital F for capital L equals 3, etc. So this is very similar to what you're used to thinking about for orbitals, but now instead of this applying just to one electron, this is for the whole set of usually valence electrons that we're considering. And these are capitalized to differentiate them from when we're talking about just a single electron. The next quantum number we have is capital S. This is the total spin angular momentum. So if we're just thinking about the spin up, spin down of our electrons that we're considering in these electron configurations. So capital S will be equal to, can be 0, right? If our total spin angular momentum, say we have one spin up and one spin down electron, that will add up overall to 0. We could possibly have a half, we could have 1, we could have 3 halves, right? And so this can increase in increments of a half, depending on which direction we have spin up, spin down, and what combination of those that we have. And then we have J, which is the total angular momentum, combining the orbital and spin angular momentum. And this is one of many cases in quantum mechanics where we can have our angular momenta what's called couple. They can basically add together. And so even though spin angular momentum is not actually electron spinning, it acts as if the electron's spinning, and that spinning can add on to this electron spinning around the nucleus, that angular momentum that's present. All right. So the way we write our term symbols, the notation that's used is we call the term capital L, and in a superscript to the left of it, we write 2 times capital S plus 1, and in a subscript to the right, we write J. And so this is the notation that we use to label electronic states of multi-electron atoms. And then we haven't defined what L, S, and J are specifically. We've kind of talked about it in general, but L is equal to right? The L vector is equal to the sum over all of our electrons for the I different electrons of the angular momentum of each ith electron, right? And I missed a word here. This is the total orbital angular momentum, and that's what makes L different than J. Okay, and so this is all the L values of each individual electron. So say we have, you know, 2 s electrons. Well, both of those L values are 0, and so capital L would also be 0. And then we also for s, so our s vector is going to be equal to the sum over all of our I electrons of the m sub s values. Oh, not the m sub s, of the s values. Okay, and our j vector is going to be equal to L plus S. So that's the combination, the total angular momentum is the combination of the orbital angular momentum that has to do with the different orbitals that are electrons in, the different L values, and then combined with the spin angular momentum. So those combine here. Now, so we can also consider the z components, and these end up mattering. So we'll list those explicitly as well. We have the LZ, capital LZ, is the sum of all the LZ values for each individual electron, which is going to be the same as the m sub s, or m sub L, let me be correct, m sub L values for each electron, and we give that the symbol capital M sub capital L. And we can do the same thing for the S component, the z component of the spin angular momentum. We can add up all the different sz values for all of our different electrons. Same thing, and this will be just the m sub s values, so the plus or minus a halves, and then we'll get a capital M sub capital S for our different z components.